This final section on buffers and titrations will cover titrations. A titration is a lab technique that is frequently used. In this technique, a known concentration of a base or an acid, something called the titrant. So in the picture here, the titrant is the base, the NaOH, okay? It's placed in a burette, and we use a burette so that we can slowly add that base to a solution of an unknown acid or base, which we have in the beaker here. That's an acid. That's known as the analyte. So we have the titrant and the analyte. The concentration of the unknown or the analyte can be determined based on the amount of the substance or the titrant that is added. So on the burette, there's these little markings for volume, and you can keep track of how much volume of titrant you're adding until you reach the equivalence point. So you know how much titrant you're adding, and you can use that to find the concentration of the unknown in the beaker. When you're setting up a titration in the lab, there are some important things to remember. First, you need to rinse the burette with distilled water. Then you need to rinse the burette with the titrant. Then fill the burette with the titrant and drain a small portion of the titrant so that there are no air bubbles near the tip of the burette, and the tip, which you can see zoomed in on here, is filled with titrant. During the titration, a pH meter or a pH indicator is used to determine when the solution has reached the equivalence point. The equivalence point is the point at which the stoichiometric amount of the acid is equal to that of the base. By using an indicator, one can visually see the solution sudden change in color. This point is also known as the end point, the point where you'll stop adding the titrant. The end point is the appearance of the first permanent color change of the indicator. And at that point, you have a slight, like 1 drop excess of the titrant in the solution. So you can see here in the example, in the first Erlenmeyer flask on the left, the indicator starts as pink. And then on the right, as we add the titrant, it goes from pink to yellow. And when you add drop by drop the titrant, when you get the very first permanent change to yellow, that's how you know you're at the end point. At the equivalence point, the number of moles of acid equals the number of moles of base. Mathematically, we can represent this as the concentration of acid times the volume of acid equals the concentration of base times the volume of the base. So if we know the concentration of, say, the acid in the burette, and we measure the volume of the acid in the burette, and of course we measure the initial volume of the base in the beaker, we can find the molarity of the unknown base in my example, right? This equation is only applicable for reactions that have a 1-to-1 mole ratio, moles of acid to moles of base. And so volume can be used for both the titrant and the analyte because the units will cancel. So when we don't have a 1-to-1 mole ratio, we'll look in a few minutes at what we have to do to take that into account. This flash animation is one that you can use to play around to determine the molarity of an acid-base solution. So you can choose either strong acid, strong base titration. You can choose weak acid or strong base titration. You can choose to fill the burette with a known acid or a known base. So if let me just choose one. Then you can fill the burette. Okay. And choose an indicator, and then drop by drop add into the flask. until you get a color change. Okay. And then, of course, you're measuring the volume here. So you can use that to help you figure out the concentration of the unknown. So here are some examples, obviously not an exhaustive list, but some examples of reactions in which the ratio of moles of acid to moles of base is 1:1. Basically, if we have a monoprotic acid, strong or weak, and a base, and here I have all strong bases, but only the group 1 metal cations in the reaction, so that we have just a single hydroxide. In reactions like this, you can use the equation MAVA equals MBVB to calculate the molarity or volume of the acid or base at the equivalence point. Here, though, are some examples of reactions where the mole ratio of acid to base is not 1:1. So here we have acid to base is 2:1, given by, you can see the coefficient of 2 in front of each of the acids. And here you can see for the base, they're all strong bases, but they're strong bases of the group 2 metals, which is how we end up with this 2:1 ratio. So I'm just going to find the ratio of moles of acid to moles of base. And so moles, remember, is MAVA, concentration times volume. So MAVA over MBVB equals, given the stoichiometric ratio, 2:1 acid to base. And then if we just cross multiply here, because we have an equation with an equal sign in the middle right here. So if we cross multiply and get this equation into a form that we're familiar with, basically if I just move this MBVB to the other side of the equation, then I get MAVA equals twice 2 MBVB. What if we have a ratio of moles of acid to moles of base that is 1:2? So this happens for our diprotic acids. And so you can see for each of the acids here, we have a coefficient of 1. And for each of these strong bases, we have a coefficient of 2. Setting up the same stoichiometric ratio, moles of acid 1 to moles of base 2, equal to our MAVA moles of acid over MBVB moles of base, we get 2 MAVA equals MBVB. All right, so here's a summary of that. If I have a 1:1 stoichiometric ratio, we just MAVA equals MBVB. If I have a moles of acid to moles of base, so this was 2:1. I just want to point something out here. I have 2:1 stoichiometric ratio base to acid. The 2 goes on the side of the equation with the acid, okay? And then here, when I had a 2:1 ratio, the 2 goes on the side of the base, okay?